The National Electrical Code (NEC) requires a grounding electrode conductor (GEC) to be installed on the secondary side of step-down transformers with a secondary voltage of 100 volts or more according to NEC section 250.24. The GEC must be sized according to the overcurrent device protecting the secondary conductors. There are several options for grounding the transformer. Firstly, ground to the main water service. This is often the preferred method. The GEC would be run from the transformer to the main water service entry point. Secondly, ground to the building steel. While the NEC allows grounding to structural steel in some cases, it is generally not recommended for buildings with bar joists or masonry walls. The bonding of bar joists is often unreliable, and the steel may not provide a low impedance path to ground. Thirdly, ground to a driven ground rod. A separate ground rod can be installed near the transformer and used as the grounding electrode. However, this method may not be as effective as grounding to the water service or building steel. While the NEC requires a GEC to be installed, a requirement for a separate ground wire run outside of the conduit may be excessive. The NEC does not specify how the GEC should be installed, and running it within the conduit would likely be sufficient. Consider the following recommendations. 1. Discuss the grounding options and try to reach a compromise. 2. If grounding to the water service is required, consider running the GEC in a separate conduit or using an insulated wire within the same conduit as the primary feeders. 3. If there are insistence on a separate ground wire outside the conduit, consult with an electrical engineer to verify the adequacy of this method. 4. Explore alternative grounding methods, such as installing a ground rod near the transformer or using a bonding strap to connect the bar joists to the main water service. When installing grounding electrode conductors, it is essential to adhere to the National Electrical Code (NEC) and local regulations. The NEC provides comprehensive guidelines for ensuring electrical safety and proper grounding techniques. Here's a detailed look at key aspects of grounding electrode conductor installation. First, NEC Article 250 covers grounding and bonding requirements. This article provides specific rules for grounding electrode systems, grounding electrode conductors, and bonding jumpers. It's essential to review Article 250 to ensure compliance with the code. Second, grounding electrode systems must comply with NEC 250.50, which outlines the requirements for grounding electrodes. Acceptable grounding electrodes include metal underground water pipes, the metal frame of the building, concrete encased electrodes, ground rings, and rod and pipe electrodes. Third, sizing the grounding electrode conductor. The size of the grounding electrode conductor is determined by NEC 250.66, which provides tables and guidelines for selecting the appropriate conductor size based on the size of the service entrance conductors or the equivalent size for parallel conductors. Fourth, the grounding electrode conductor must be connected to the grounding electrode using approved methods and connectors. For example, when connecting to a metal water pipe, the connection must be made within 5 feet of the point where the water pipe enters the building. Fifth, protection of the grounding electrode conductor. NEC 250.64 requires the grounding electrode conductor to be protected from physical damage. This protection can be achieved by running the conductor through conduit or other protective means. Sixth, continuous and unbroken conductor. The grounding electrode conductor must be continuous and without splices or joints, unless specifically permitted by the NEC. Any splices must be made using irreversible compression connectors or exothermic welding. Seventh, auxiliary grounding electrodes. In some cases, auxiliary grounding electrodes, such as ground rods or plates, may be required to supplement the primary grounding electrode. These auxiliary electrodes must meet the requirements of NEC 250.53. 8. Grounding at multiple buildings. When multiple buildings are supplied from a common service, each building must have its own grounding electrode system, as specified in NEC 250.32. The grounding electrode conductor must be sized and installed in accordance with the NEC requirements for each building. 9th. Grounding of transformers. For separately derived systems, such as transformers, The grounding electrode conductor must be connected to the neutral point of the equipment grounding bus of the transformer. The size of the grounding electrode conductor is determined by NEC 250.30 and 250.66. 10th. Documentation and labeling. It is essential to document the grounding electrode system and label the grounding electrode conductor. This documentation should include the location of the grounding electrodes, the size and type of grounding electrode conductor, and the methods used for connection and protection. Proper labeling helps facilitate future inspections and maintenance. The requirements for grounding electrode conductors vary depending on the specific application and the type of grounding electrode being used. Always consult the latest edition of the NEC and local regulations to ensure compliance. Proper grounding is crucial for electrical safety, protecting equipment and personnel from electrical faults and ensuring the reliable operation of electrical systems. When grounding to a metal water pipe, the connection must be made within 5 feet of where the pipe enters the building. This ensures the grounding system effectively utilizes the conductivity of the water pipe. Ground rods should be at least 8 feet long and driven into the ground. They should be spaced at least 6 feet apart to provide effective grounding. Concrete encased electrodes, often called UFA grounds, must be at least 20 feet long and encased within at least 2 inches of concrete. These are typically installed during the construction of a building's foundation. Ground rings encircling the building must be buried at least 30 inches below the surface and consist of at least 20 feet of bare copper conductor. The size of the grounding electrode conductor is crucial for effective grounding. For example, if the service entrance conductors are 4/0 American wire gauge copper, the grounding electrode conductor to a ground rod or plate should be at least number 6 American wire gauge copper. If the service entrance conductors are 250 kcmil copper, the grounding electrode conductor to a ground rod or plate should be at least number 4 American wire gauge copper. For service entrance conductors larger than 250 kcmil copper, refer to NEC Table 250.66 for the appropriate grounding electrode conductor size. Aluminum or copper-clad aluminum conductors have different sizing requirements. Always consult NEC Table 250.66 for correct sizing. When using metal conduit to protect the grounding electrode conductor, the conduit must be bonded to the conductor at both ends to ensure electrical continuity. This bonding is typically achieved using grounding bushings or bonding lock nuts. If the grounding electrode conductor is exposed to physical damage, it should be protected by rigid metal conduit, intermediate metal conduit, or other approved means. The NEC requires that the grounding electrode conductor be continuous and without splices. However, if a splice is necessary, it must be made using reversible compression connectors listed for grounding, unbonding, or by exothermic welding. Grounding electrode conductors must be securely fastened to the surface on which they are carried. Use straps, clamps, or other approved means to support the conductor and prevent it from being damaged or disconnected. Auxiliary grounding electrodes, such as ground rods, must be located at least 6 feet away from other grounding electrodes, such as metal water pipes or building steel. This spacing minimizes the risk of interference between the electrodes. When grounding multiple buildings supplied from a common service, each building must have its own grounding electrode system. The grounding electrode conductors for each building must be sized and installed according to the NEC requirements. For separately derived systems, such as transformers, the grounding electrode conductor must be connected to the neutral point of the equipment grounding bus of the transformer. This connection ensures that the system is properly grounded and that fault currents can flow safely back to the source. The size of the grounding electrode conductor for a transformer is determined by the size of the transformer's secondary conductors. Consult NEC Tables 250.30 and 250.66 for the correct sizing requirements. Accurate documentation and labeling of the grounding electrode system are essential for future maintenance and inspections. The documentation should include the location of all grounding electrodes, the size and type of grounding electrode conductors, and the methods used for connection and protection. Label the grounding electrode conductor with a permanent marker or label maker to identify its purpose. Ensure the label is visible and legible. Regular inspection and maintenance of the grounding electrode system are crucial for ensuring its continued effectiveness. Inspect the grounding electrode conductors for signs of corrosion, damage, or loose connections. Test the grounding electrode system periodically to verify its resistance to ground. A low resistance to ground indicates a more effective grounding system. If the grounding electrode system is found to be deficient, take corrective action immediately to restore it to proper working condition. This may involve replacing damaged conductors, tightening loose connections, or adding additional grounding electrodes. Always consult with a qualified electrician or electrical engineer when installing or maintaining grounding electrode systems. They can provide valuable guidance and ensure that the system is installed and maintained in accordance with the NEC and local regulations. Grounding electrode conductors play a critical role in electrical safety. By following the NEC guidelines and best practices for installation and maintenance, ensure electrical systems are properly grounded and protected from electrical faults. Proper grounding helps to minimize the risk of electric shock, equipment damage, and fire hazards. Understanding the requirements for grounding electrode conductors is essential for anyone involved in the design, installation, or maintenance of electrical systems. Grounding electrode conductors are a vital component of any electrical system. Grounding electrode conductors provide a low impedance path for fault currents to return to the source, helping to protect people and equipment from electrical shock and damage. The size of the grounding electrode conductor depends on the size of the service entrance conductors. Refer to NEC Table 250.66 to determine the appropriate size. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods. Common grounding electrodes include metal water pipes, ground rods, and building steel. Grounding electrode conductors must be protected from physical damage. Use conduit or other protective measures to prevent damage. Regular inspection and maintenance are essential to ensure that grounding electrode conductors are functioning properly. Check for corrosion, loose connections, and physical damage. The grounding electrode conductor must be continuous and without splices. If a splice is necessary, it must be made using an approved method. Grounding electrode conductors must be identified with a green color or with green tape. This helps to distinguish them from other conductors. When grounding to a metal water pipe, the connection must be made within the first 5 feet of the pipe's entrance to the building. This ensures that the grounding system is effective. Ground rods must be driven at least 8 feet into the ground. They should be spaced at least 6 feet apart. Building steel can be used as a grounding electrode if it is effectively grounded. The steel must be connected to the grounding electrode conductor using approved methods. Concrete encased electrodes, also known as UFA grounds, are another effective grounding method. These electrodes must be encased in at least 2 inches of concrete. Ground rings are another option for grounding. They must be buried at least 30 inches below the surface of the earth. Grounding electrode conductors must be installed in a neat and workmanlike manner. This helps to ensure that the system is safe and reliable. Grounding electrode conductors must be protected from corrosion. Use corrosion-resistant materials or coatings to prevent corrosion. Grounding electrode conductors must be accessible for inspection and maintenance. Avoid burying them or covering them with obstructions. Regular testing of grounding electrode conductors is recommended to ensure that they are functioning properly. Use a ground resistance tester to measure the resistance of the grounding system. If the resistance is too high, take corrective action to improve the grounding system. Grounding electrode conductors are an essential part of any electrical system. By following these guidelines, ensure that systems are properly grounded and protected from electrical hazards. It is essential to understand local electrical codes, which may have specific requirements for grounding electrode conductors. The National Electrical Code, NEC, provides a comprehensive set of guidelines for grounding and bonding. It is crucial to consult the NEC for detailed requirements and best practices. Grounding electrode conductors help to minimize the risk of electrical shock, equipment damage, and fire hazards. By ensuring that electrical systems are properly grounded, create a safer environment for people and equipment. The principles of grounding electrode conductor installation apply to a wide range of electrical systems, including residential, commercial, and industrial applications. Different types of buildings and structures may have unique grounding requirements. Consult with a qualified electrical engineer or electrician to determine the best grounding solution for a specific application. Effective grounding electrode conductors are essential for reliable electrical system performance. Grounding electrode conductors help to stabilize voltage levels, reduce electrical noise, and improve the overall quality of electrical power. Properly installed grounding electrode conductors can help to prevent electrical equipment malfunctions and extend the lifespan of electrical equipment. Grounding electrode conductors play a vital role in lightning protection systems. Grounding electrode conductors provide a path for lightning currents to flow safely to ground, minimizing the risk of damage to buildings and equipment. The proper selection and installation of grounding electrode conductors is critical for ensuring the effectiveness of lightning protection systems. Grounding electrode conductors are an important part of surge protection systems. Grounding electrode conductors provide a path for surge currents to flow safely to ground, protecting sensitive electronic equipment from damage. Effective grounding electrode conductors are essential for minimizing the impact of power surges and voltage transients. Grounding electrode conductors help to reduce electromagnetic interference (EMI). Grounding electrode conductors provide a path for EMI currents to flow safely to ground, preventing them from interfering with sensitive electronic equipment. The proper installation of grounding electrode conductors can help to improve the performance of electronic systems and reduce the risk of EMI-related problems. Grounding electrode conductors are essential for maintaining a safe and reliable electrical system. By following these guidelines, ensure that electrical systems are properly grounded and protected from electrical hazards.